These are your 9.3b notes, standard form to vertex form. We just spent the last couple days understanding vertex form, putting equations into vertex form, if they were sort of written in that way, and then analyzing what do those values of A, H, and K do to the graph. So now I want to just compare the two forms that we know for quadratics and what you can get from the equation. When an equation is given in standard form, to find the vertex, you have to do the negative b over 2a value to get that first part of that vertex. So you have to do a little bit of math, a little bit of calculating. It's easy math, but as you can see through that project, it's easy to make mistakes as well. To get the y coordinate, you have to plug this value in for x everywhere in the equation. Your axis of symmetry is that same value, x equals negative b over 2a. And then your y-intercept is the one thing that this thing tells us pretty straightforward. And you just look at it and you have the c value. So the standard form is really good for y-intercept. You can also tell by the sign of the a value, if it's a positive a, it's going to open upward, and so you have a minimum. If it's a negative a, it's going to open upside down, and then you're going to have a maximum value. So just by looking at the equation, you can get the y-intercept, and you can tell if it's a min or a max based on the sign of a. When equations are in vertex form, what's nice about vertex form is you're looking at the vertex. So the vertex, when it's in vertex form, is the values h and k. You're staring at the vertex, but you don't have your y-intercept anymore. The k value is not your y-intercept. There's some other numbers that would be added or subtracted from that k value if you squared that quantity and multiplied the a. So you can't get the y-intercept from it, but you can get the vertex from it. The other thing that we can get is obviously the axis of symmetry. If the vertex is sitting on the axis of symmetry, it's the equation x equals h. And then the same thing with the positive a and the negative a. If it's positive, it's going to be a min. If it's negative, it's going to be a max. But we can also talk about the size in either case, whether it's narrower or wider. But just by looking at the equation, these are the different things you can get. So now what we're going to do is this lesson is concentrating on what if they give us the standard form and we want to put it into vertex form. We're going to change from one form to the other. And so they're a little bit different. The biggest concern is bringing in that x minus h squared piece right here. We got to bring in a quantity squared. And I'm going to show you just a quick little thing that we did back when we were factoring. Sometimes trinomials actually end up being a nice perfect square like that. And so to convert, one of the very first things that we have to do is we're going to move c to the other side of the equation. We're going to move out the old c and bring in a better perfect c. We're going to make these perfect squared trinomials, and that's the thing I need to review real quick. We're going to calculate the new perfect c value and add it to both sides. So before I continue on with this, I want to just bring us back to factoring. When we were factoring, we had times where we had a trinomial, and we could guess and check to get this answer, or we could use a product sum table or the squares, whatever it may be. But we were looking for a quantity that you multiply by itself to get that trinomial. And so to get an x squared, I knew it was x and x. And to make 16 and 8, it was a positive 4 and a positive 4. And anytime we got the quantity the same, we would just write it as a quantity squared. So what I just did there was I made something that looks really similar to standard form, a trinomial, and then I created a quantity squared, like vertex form. So this is a process that we're going to have to use to make standard form get into vertex form. We're going to factor. And what we're going to make it a perfect square trinomial. Not every standard form is going to be perfect, so we're going to force it to be perfect. So this is the part that if it isn't, this is the perfect C value that I was talking about. We're going to calculate the new perfect C value, and we're going to bring it into both sides. That value has to be half of the B value squared. So the new perfect C value is equivalent to half of the B value squared. It looks really ridiculous, but I'll explain in a little bit. And we add it to both sides because as long as you change one side of the equation, you can change the other side of the equation and everything will be the same. So we're going to move out the old C. This one's non-perfect. We're going to get rid of it and make room for a new C value. And the whole reason we bring in this value is it'll create a perfect square trinomial. And so when you factor the newly created perfect square trinomial, we're going to get the x minus h squared that we were looking for. That's what brings in that quantity squared that we need. And after we get that wonderful quantity, we're going to bring back the C value that we threw out. We're going to bring it back, and it's going to become part of K. It won't necessarily be K. It'll change its value, and you'll see how that works. So let's go ahead and just try it. So you can always refer to those steps. Anytime you get stuck, you can go back through your notes and read them step by step, and it's like a checklist. So we're going to write the following in vertex form, then we're going to come up with all the information of the function. Okay, so looking at this first one, this is in standard form. We've got my A value is 1, my B value is -8, and my C value is 6. I look at that and I know it's not a perfect square trinomial because I can't multiply to get some 6 and add to give -8. It's not going to factor to something pretty. Up here, I'm just going to write what our goal is. Our goal is to get those equations, those forms to look like this. So the very first thing we're going to work on is this part. So I want a value here that makes this whole thing perfect. So I'm going to move that out. So how I move it out is I'm going to subtract 6 from both sides. So I get y minus 6 is equal to x squared minus 8x. Well, now I no longer have a trinomial. So when I move out the old ugly C, I need to bring in a new C. And the new C value, my new perfect C, is taking half of the B value and squaring it. So I'm just going to write that down for you. So we're going to take the -8, that's our B value, take half of it, and I get -4. Square the -4, and I get a positive 16. That's the C value that will make this a perfect square trinomial. So I'm going to add 16 to this side, and I'm going to add 16 to the other side. So what we'll have is y minus 6 is there. I'm going to add my new perfect 16 to the one side, which allows me to add it to the other side as well. In equations, as long as you're consistent, I made the left side 16 bigger, I made the right side 16 bigger, it's still equivalent. By doing that, that creates, this becomes a perfect square trinomial. So now I need to factor that perfect square trinomial. So what multiplies to give me 16 and adds to give me -8 is x minus 4 times x minus 4, or the quantity x minus 4 squared. If you remember the shortcut from factoring, we square root the first term, which is x. We square root the last term, which is 4, and then we would take the sign of the middle term and then call it squared. So that was just a little shortcut of factoring. But in the end, this is the whole reason we added 16, is so that the trinomial became something squared. The left-hand side of this equation, I'm going to clean up, and I'm going to add 16 and -6. So I get y plus 10. I'm almost there. I'm starting to see my vertex form show up. I can't leave this y with this 10, so I need to move the 10 over. So I'm going to subtract 10 from both sides. y is equal to x minus 4 squared minus 10. Now I have vertex form. The only thing missing is if you wanted to put an a value of 1 out in front there, that would be fine. So from that, I should be able to evaluate all of the information. So my vertex is 4, negative 10. The direction of opening is up. It's opening up. I do a little sketch, and that tells me that this is a minimum value. And that means that negative 10 is the smallest value. My axis of symmetry is x equals 4. My domain is all reals. And because it's a minimum value, that means that my range, my y values, will be greater than or equal to negative 10. They will never go beyond negative 10. And what else did I ask for? I think that's it. Notice I didn't ask for the y-intercept, and I could put y-intercept on there, but my y-intercept I actually have to find using the original problem. So 6 is my y-intercept. My y-intercept is 0, 6. It's not the negative 10. Negative 10 is my vertex. That's my k value. My c value comes from the original. And that is, in a nutshell, completing the square. So we're putting it in vertex form. It's called completing the square because we made it a perfect square. We took a trinomial that was not perfect and we made it perfect. So let's look at number 2. A little repetition here. I need to move out old c. I'm going to bring old c over, and I'm going to try at the same time to maybe leave room for a new c. So I'm going to do it a little bit different. I'm going to add 12 to the y value. Then I'm going to add a blank. That's where my new c value is going to go. Is equal to x squared plus 2x plus blank. All I'm doing is I'm kind of combining the first 2 steps that I did in the last problem. I'm leaving space so that I can add 16. I moved over the negative 6. Now I want to add 16. I'll just do it all in one step. So before I can add anything to it, I need to use this value right here, go off to the side, take half of my b value, which is 1, and square it. And that's equal to 1. So to make this a perfect square trinomial, I need to add 1 to it. If I add 1 to one side, I have to add 1 to the other side to keep it balanced. Now let's clean up. And so 12 plus 1 is 13. Y plus 13 is equal to, I need to factor this. So when I factor this trinomial, what multiplies to give me x and adds to give me a positive 1, or multiplies to give me 1 and adds to give me 2, that's what I want to say, is x plus 1 times x plus 1. I'm almost done. We need to move this 13 over to the other side. Y is equal to the quantity x plus 1 squared minus 13. The vertex is negative 1, negative 13. My axis of symmetry is x equals negative 1. This parabola is opening upward, and so it's a minimum again. My domain is all reals. The range will not go beyond the negative 13. That is the lowest point on the graph. So my y values are greater than or equal to negative 13. And one last value, my y-intercept I can get from the original is negative 12. Or if you wanted 0, negative 12. That's your c value. Okay? I'm going to skip over number 3. I'm going to go right into number 4 because in number 4, my b value is odd. So when we take half of that b value and square it, it's going to be an ugly fraction. But in the end, it all cleans up. All right, so I'm going to move out old c. Y plus 7 plus a space for my new c, my new perfect c, is equal to x squared plus 3x plus new perfect c. To figure out what my new perfect c value is, I need to work with this value right here. I'm going to take half of 3, and because it doesn't turn into a half, I'm just going to leave it as 3 halves. I'd like you guys to leave it as a fraction. It's so much easier. Because then when you square a fraction, you don't have to worry about all these decimals. You square the top, you get 9, and you square the bottom, and you get 4. So I'm actually going to get 9/4. I'm just going to make that answer blank, my little fraction bar, 9/4, 9/4 to both sides. Now it looks ugly, I get that, but I'm going to show you how awesome this is. Leave it as a fraction, square the fraction. Okay, this becomes the hardest math problem. Okay, use your calculator if you need to. I like to get a common denominator. I rewrite this as fourths. That's 28/4 plus 9/4 is equal to 37/4. No big deal. And then I'm going to set that equal to, I need to factor this to become something squared. Well, the square root of x squared is x. The square root of 9/4, you're staring at it. The number inside these parentheses is always your value here. And so you can just simply put 3/2, or take the square root of 9 is 3 and the square root of 4 is 2. The sign of the middle is positive. So I didn't need a calculator, I just squared them, but then I just took the square root of it later on. The last thing we need to do is we need to move this ugly number over. But in life and in these parabolas, they're not always nice and pretty. And so this vertex is pretty ugly. This vertex is at -3/2, -37/4. Remember, it's always, it looks like the opposite sign. Your h value that's plugged in there to make it a positive must have been negative. So it's a -3/2 and a -37/4. My axis of symmetry is x equals -3/2. This opens upward. We're going to do a lot of opening up because if not, it's a little difficult. That means we have a minimum value, and my domain is all reals. And my range is y has to be greater than or equal to -37/4. You'll never go beyond that. And there's everything about that function. So I skipped number 3 because I just feel like it's monotonous. My y-intercept, I didn't talk about it, but the y-intercept here would be -7 in that original problem. All right. So as a lesson summary, I'd like you to figure out the c value. Just do that b divided by 2 squared. Tell me what would make that a perfect square trinomial. You don't have to do anything else with it. And then the practice problem, I want you to actually put that in vertex form. Go through all the steps, show all the work, and put it in vertex form. Good luck.